Welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Let's learn together. In this video, we'll be tackling question 4 from a past exam paper, which focuses on differential equations. This is a key part of the N6 syllabus, and mastering it will build a strong foundation for your future studies. Our objective today is to learn how to solve two specific types of differential equations. You will be able to determine the general solution of a first-order linear differential equation, and you will also be able to find the general solution of a second-order non-homogeneous linear differential equation. Let's dive right into our first problem. Our first problem is question 4.1. The question asks us to determine the general solution of the equation di or dx minus 3i equals 3x squared e to the power of x. First, let's identify what kind of differential equation this is. We can see it contains a first derivative, dx, so it's a first-order equation. It fits the standard form for a first-order linear differential equation, which is dx plus a function of x times y equals another function of x. Comparing our equation, dx minus 3 equals 3x squared e to the x, we can see that px is 3 and qx is 3x squared e to the x. So it is indeed a first-order linear differential equation. To solve this type of equation, the standard method is to use an integrating factor. This is a special function that, when multiplied throughout the equation, makes the left-hand side perfectly integrable. The formula for the integrating factor, often abbreviated as IF, is e to the power of the integral of p of x dx. Let's apply this to our problem. Remember, peak x is 3, so the integrating factor is e to the power of the integral of negative 3 dx. The integral of a constant is just the constant times x, so the integral of 3 dx is 3x. This gives us our integrating factor, e to the power of negative 3x. Great! Now we take this integrating factor and multiply it by every term in our original differential equation. Let's make sure we do this carefully to avoid common algebraic mistakes. Multiplying through, we get e to the negative 3x times dx minus 3y times e to the negative 3x equals 3x squared e to the x times e to the negative 3x. On the right-hand side, we can combine the exponentials. E to the x times e to the negative 3x is e to the x minus 3x, which simplifies to e to the negative 2x. So the right side becomes 3x squared e to the negative 2x. Now here's the magic of the integrating factor. The entire left-hand side is now the exact derivative of a single product. Y times the integrating factor, y to the negative 3x. This is a crucial step. You can verify this using the product rule. The derivative of ye to the negative 3x is dx times e to the negative 3x, plus y times the derivative of e to the negative 3x, which is y times negative 3 times e to the negative 3x. This is exactly what we have on the left. To solve for y, we now integrate both sides with respect to x. So ye to the negative 3x equals the integral of 3x squared e to the negative 2x dx. On the left, the integral and the derivative cancel out, leaving us with ye to the negative 3x. Our main task is now to solve the integral on the right. So we have the equation e to the negative 3x equals 3 times the integral of x squared e to the negative 2x dx. This integral requires a special technique called integration by parts. Our objective in this scene is to perform the integration by parts to solve the remaining integral. The integral we need to solve is the integral of x squared times e to the power of negative 2x dx. The problem states this will require integrating by parts twice. The formula for integration by parts is the integral of u dv equals uv minus the integral of v dv. The key is choosing our u and dv correctly. A helpful mnemonic is Li8, which stands for logs, inverse trig, algebra, trig, exponentials. This gives us a priority order for choosing u. Since x squared is an algebraic term, a and e to the negative 2x is an exponential term, e, we should choose u to be the algebraic term. So we'll set a equal to x squared. Then we find the derivative, do, which is 2x dx. We set dv equal to the rest of the integral, e to the negative 2x dx. To find v, we integrate dv. The integral of e to the negative 2x is negative 1/2 e to the negative 2x. Now we substitute these into our integration by parts formula. So, the integral of x squared e to the negative 2x equals u times v, which is x squared times negative 1/2 e to the negative 2x, minus the integral of vs, which is the integral of negative 1/2 e to the negative 2x times 2x dx. Simplifying, the first term is negative 1/2 x squared e to the negative 2x. In the integral, the 2 in the do term and the negative 1/2 in the v term cancel, and the two negatives multiply to make a positive. This leaves us with a new integral. The integral of x e to the negative 2xd. We're not quite done. We still have an integral to solve, this time with x instead of x squared. We need to apply integration by parts again. For this new integral, the integral of x e to the negative 2x dx, we repeat the process. Let u be x, so do is dx. Let dv be e to the negative 2xd, so v is still negative 1/2 e to the negative 2. Applying the formula again, the integral of x e to the negative 2x equals x times negative 1/2 e to the negative 2x, minus the integral of negative 1/2 e to the negative 2x d. Now we're down to a simple integral we can solve directly. The first term is negative 1/2 x e to the negative 2x. For the integral, the two negatives become a positive 1/2, and the integral of e to the negative 2x is negative 1/2 e to the negative 2x. Multiplying the 1/2 and negative 1/2 gives us negative 1/4 e to the negative 2x. Excellent. We have now solved both integrals. Our objective for this scene is complete. In the next scene, we will combine these results to get our final general solution. We've reached the final step. Our objective is to combine all the pieces we've calculated to find the general solution for y. Let's recall the equation we had. Y times e to the negative 3x equals 3 times the integral of x squared e to the negative 2x dx. In the previous scene, we found the solution to the integral. Let's substitute that back in. So y e to the negative 3x equals 3 times the expression we found from integrating twice by parts. Negative 1/2 x squared e to the negative 2x, minus 1/2 x e to the negative 2x, minus 1/4 e to the negative 2x. Don't forget to add the constant of integration, c. Now let's distribute the 3 across the terms in the square brackets. This gives us negative 3 over 2 by x squared e to the negative 2x, minus 3 over 2 x e to the negative 2x, minus 3 over 4 e to the negative 2x, all plus c. We are very close to our final answer. The equation is currently in terms of y times e to the negative 3x. We want to find y on its own. To do this, we multiply every single term in the equation by e to the power of positive 3x, multiplying each term by e to the 3x. On the left, the exponentials cancel, leaving just y. On the right, e to the negative 2x times e to the 3x becomes e to the x. So our final general solution is y equals negative 3 over 2 x squared e to the x, minus 3 over 2 x e to the x, minus 3 over 4 e to the x, plus c e to the x. Let's compare this to the provided memo. The memo gives an answer of negative 3 over 2 ls squared e to the x, minus 3 over 2 x e to the x, minus 3 over 4 e to the x plus c. The only difference is the memo has c, while our answer has c e to the 3x. This is not a mistake. Since c is an arbitrary constant, c times e to the 3x is still just an arbitrary constant, which we could call k for instance. So, the two answers are mathematically equivalent and both correct. The memo writer likely just absorbed the e to the 3x into the constant, which is a common and acceptable practice. We have successfully determined the general solution for the first problem. Objective met. Now let's move on to our second problem, question 4.2. The question asks for the general solution of the second derivative of y plus 6 times the first derivative of y plus 9y equals x squared. This is a second-order equation because of the d squared e over dx squared term. It's a non-homogeneous linear differential equation with constant coefficients. We know it's non-homogeneous because the right-hand side, x squared, is not equal to 0. If it were 0, it would be homogeneous. Solving these equations involves two main steps. The general solution, which we call y, is the sum of two parts. The complementary solution, y2, and the particular solution, y'. The complementary solution, yc, comes from the associated homogeneous equation where the right side is 0, and the particular solution, ycp, is found based on the form of the non-homogeneous term. Let's begin with the first part, finding the complementary solution, sac. Our objective is to determine yc from the associated homogeneous equation. To do this, we first solve the associated homogeneous equation, which is d squared e over dx squared plus 6 times dx plus 9y equals 0. We solve this using the characteristic equation, which is an algebraic equation. We replace d squared e over dx squared with r squared, d dx with r, and y with 1. This gives us the characteristic equation, r squared plus 6r plus 9 equals 0. Now we need to solve this quadratic equation for r. We can notice that this is a perfect square trinomial. It factors nicely into the quantity r plus 3 squared equals 0. Solving for r, we find that r equals -3. This gives us a repeated root. The roots are identical. The type of roots we find determines the form of the complementary solution, y's. For repeated roots, like we have here, there is a specific formula. When we have two equal roots, yc is given by a plus bx, all multiplied by e to the power of rx, where r is our repeated root. Plugging in our repeated root r equals 3, we get the complementary solution. Yc equals a plus bx at e to the -3x. Here a and b are arbitrary constants determined by initial conditions which are not provided in this problem. So we have now found our complementary solution. That's one part of our general solution. Our objective for this scene is complete. Now for the second part, finding the particular solution, yp. The objective here is to determine yp based on the right-hand side of our original equation. Remember our full equation, d squared e over dx squared plus 6 times dx plus 9e equals x squared. Our particular solution yp must account for the right-hand side x squared. We use the method of undetermined coefficients. The idea is to guess the form of the particular solution based on the non-homogeneous term. Since the right-hand side is a polynomial of degree 2, our guess for yp should be a general polynomial of degree 2. So we guess that yp has the form c ex squared plus dx plus e. Here c, d, and e are constants that we will determine. Notice that this form of yp does not contain any parts from our complementary solution yc, so there is no need for modification. For this to be a solution, it must satisfy the original differential equation. This means we need its first and second derivatives. Let's calculate them. The first derivative, yp prime, is 2cx plus d. The second derivative, y hat double prime, is 2c. Now we substitute ycp prime and ycp double prime back into the original differential equation. So we have 2c plus 6 times the quantity 2cx plus d plus 9 times the quantity cx squared plus dx plus e, and this must all equal x squared. Let's expand the terms and group them by powers of x. This is where most students make small calculation errors, so let's be careful. Expanding the equation gives us 2c plus 12ac plus 6d plus 9cx squared plus 9dx plus 9e equals x squared. Grouping the terms gives us 9cx squared plus the quantity 12c plus 9d times x plus the quantity 2c plus 6d plus 9e, all equal to x squared. For these two polynomials to be equal for all x, the coefficients of the corresponding powers of x must be equal. We call this equating coefficients. First, the coefficient of x squared. On the left we have 9c, and on the right we have 1. So 9c equals 1. Next, the coefficient of x. On the left it's 12c plus 9d, and on the right, since there's no x term, it's 0, 0. So 12c plus 9d equals 0. We can substitute our value c equals 1 9 into this equation. This gives 12 times 1 9 plus 9d equals 0. 12 ninths simplifies to 4 thirds. So 4 thirds plus 9d equals 0. Subtracting 4/3 and dividing by 9, we get d equals -4/27. Finally, we look at the constant terms. On the left, it's 2c plus 6d plus 9e, and on the right, it's 0. Substituting our values for c and d, we get 2 times 1, 9, plus 6 times -4/20 plus 9e equals 0. This simplifies to 29 minus 247, plus 9e equals 0. Simplifying further to a common denominator of 27, we get 627 minus 247, plus 9e equals 0, which is -1827, plus 9e equals 0. -1827 simplifies to -2 or 3. So -2 to 3 plus 9e equals 0. Adding 2 to 3 and dividing by 9 gives us e equals 2/7. We've found our constants c, d, and e. Substituting these values back into our guess for y sub p, we get the particular solution. Yap equals 1/9cx squared minus 4/27x plus 2/27. We have now successfully determined the particular solution, meeting our objective for this scene. Now for our final scene. The objective is to combine our complementary and particular solutions to form the general solution. This is the easiest step, as we've done all the hard work already. Remember that the general solution is simply the sum of the complementary solution yc and the particular solution yp. We found the complementary solution to be a plus bxe to the -3x, and we found the particular solution to be 190x squared minus 427x plus 2/27. Therefore, the general solution is y equals a plus bxe to the -3x plus 19x squared minus 427x plus 2/27. This is our complete and final answer. Let's compare this with the provided memo. The memo gives y equals e to the -3x times the quantity a plus bx plus 189x squared minus 427x plus 2/27. Our answer is identical. The order of the terms might be slightly different, but it contains the exact same components, which is what matters. Objective met. Let's quickly recap what we did. For the first problem, we identified a first-order linear equation, found an integrating factor, and used integration by parts twice to solve the resulting integral. For the second problem, a second-order non-homogeneous equation, we first solved the homogeneous part to find yc, then used the method of undetermined coefficients to find yp, and finally added them together to get the general solution. These are fundamental methods in solving differential equations in Mathematics N6. Thank you for watching. Like, subscribe, and continue learning with earthly teachings.